Welcome to AI Paper Podcasts. Today we're diving into some really exciting research, a paper called A Survey of Reinforcement Learning for Large Reasoning Models. This one comes from a big collaboration, Tsinghua University, Shanghai AI Lab, others, and it's all about how AI reasoning is, well, fundamentally changing.
Yeah, it's a big topic. We've all seen how amazing large language models, LLMs, have become, right? Text generation, coding help, answering questions. But when you throw really complex multi-step logical problems at them, think tricky math proofs or debugging tangled code, they often just stumble. That's been the weak spot.
Exactly, and that limitation is precisely what the survey tackles head-on. It maps out how reinforcement learning, RL, is evolving these LLMs into something new. They're calling large reasoning models, or LRMs, and the core idea, the thing to really grab onto, is that RL, specifically with Verifiable Rewards, RLVR as they call it, that's the magic key, it unlocks sophisticated, reliable reasoning.
Right. So if you need the quick takeaway, RLVR is making LLMs truly think. We're seeing models like DeepSeek R1, OpenAI's O1. They use these verifiable rewards. Things like, was the math answer correct? Did the code pass the unit tests? And that lets them do much more advanced stuff, planning, reflecting, even fixing their own mistakes.
And what's really groundbreaking here is this idea of a new scaling axis. Performance isn't just about making models bigger anymore. It also scales with more RL training compute. And this is crucial, more thinking time during inference. It's like a whole different way to get smarter AI.
Absolutely. It really points towards potentially unprecedented capabilities in complex problem solving. But, it's not all smooth sailing. The survey is pretty clear about the challenges. We need better algorithms, much better training data, especially data you can verify, and stronger infrastructure. It's not just about throwing more GPUs at it.
Okay, so our mission today, unpack all of this, get into the nuts and bolts of RL for these LRMs, understand how it works, and think about where this is all heading. Maybe even towards truly advanced AI for reasoning. Let's dig in.
Sounds good.
All right, let's start right at the beginning. The fundamental why. Why do standard LLMs struggle so much with these really complex logical tasks?
Well, it really boils down to how they're trained initially. Your typical LLM learns by predicting the next word, right, over and over, on massive data sets. That makes them incredibly good at recognizing patterns, generating fluent language, sounding human. But that process doesn't explicitly teach them sequential logical deduction. For, say, solving a math problem step by step or finding a bug in code, they don't have a built-in mechanism to learn and fine-tune the actual process of reasoning. They often just guess the most plausible sounding answer based on patterns.
It's like they're good mimics, but not necessarily deep thinkers for certain kinds of problems.
Exactly. The paper talks about mode covering behavior.
Yeah.
They try to cover all the plausible answers they saw in training, instead of reliably finding the single correct logical path.
Okay, and that's where reinforcement learning comes in as a potential fix, offering a totally different learning paradigm. Just a quick refresher for everyone. RL involves an agent learning through trial and error in an environment, trying to maximize some kind of reward.
Yeah, think of teaching a robot to walk. It tries things, falls down, gets a negative reward, tries something else, stays up longer, gets a positive reward. It learns by doing and getting feedback.
And this maps surprisingly well to language models, doesn't it?
It really does. The prompt you give the LLM, that's basically the starting state, the environment context, the LLM itself. That's the policy. It decides what to do next. Each token, each word it generates is an action. And as it generates more tokens, the state evolves. The conversation or the solution it's building changes.
So it's not just predicting the next word in isolation, it's making a sequence of choices, like steps in a logical argument or lines of code.
Precisely. And the reward tells it if that sequence of choices led somewhere good. Did it solve the math problem? Did the code compile?
And this is where RLVR, that reinforcement learning with verifiable rewards, becomes so powerful. It's not just about making the output sound good or seem preferred by humans, like traditional RLHF tries to do. RLVR is about explicitly rewarding correct reasoning, using things you can objectively check. Is the math answer verifiable? Does the code pass the tests? That gives the model a really clear, strong signal to improve its actual logical thinking.
That clarity is key. No ambiguity, just right or wrong.
Okay, so with that foundation laid, let's break down the essential pieces that make this work. First up, reward design. This seems critical. How do you actually tell the LLM if it's reasoning well, especially for complex stuff?
Reward design is, absolutely make or break. For tasks where there's a definite right answer, like math or coding. Verifiable rewards are basically the gold standard. These are rule-based. Use external tools. The paper mentions things like Math Verify, SIMPy for math, or just compilers and unit tests for code to automatically check correctness. And this leads to what the paper calls Verifiers Law, which I think is a great term. Basically, the easier a task is to verify automatically, the faster RL can make the model better at it.
That makes total sense. Clear feedback equals faster learning. But what about tasks that aren't so black and white, like judging the quality of a story or maybe the persuasiveness of an argument? You can't just run a unit test on that.
Right. For those more subjective areas, the paper discusses generative rewards. This is pretty fascinating. You can actually use another LLM to act as a judge or critic. It might use a detailed rubric or even just natural language feedback to evaluate the output of the main LLM. Sometimes you even train the main model, the policy, and the reward model together. They sort of co-evolve.
Huh. Using an LLM to judge another LLM. Interesting. Now, whether these rewards are verifiable or generative, they often come at the very end, right? You solve the whole problem, then you find out if you got it right. That seems slow.
It can be, yeah. That's the sparse reward problem. And it leads to the idea of dense rewards. Instead of waiting till the end, you provide feedback more frequently, maybe after each step in a math proof or each turn in a dialogue. This really helps with what's called the credit assignment problem, figuring out which specific action early on led to the final success or failure. Dense rewards make training much more efficient and stable.
Like getting feedback on your code line by line instead of only when you try to compile the whole thing.
Exactly like that. It shortens the feedback loop dramatically.
Okay, and one more type of reward. Unsupervised rewards. This sounds like the dream, getting reward signals without needing humans to label everything. How does that work?
Unsupervised rewards are crucial for scaling this all up. The idea is to generate signals based on the model's own behavior or properties. Things like internal consistency, maybe its own confidence score, or using external heuristics. It's powerful because you bypass the human bottleneck. But there's a definite risk: reward hacking. The model might find a clever way to maximize this unsupervised signal without actually getting better at the task you care about. It's a tricky balance.
Right. Optimizing for the proxy metric instead of the real goal. Okay, so we have ways to give feedback. Now let's talk policy optimization. How does the LLM actually use these rewards to learn and improve its strategy, its policy?
So the goal is always to maximize the total expected reward over time. Usually you also add some kind of regularization to keep the model from, forgetting how to generate normal language. The algorithms generally fall into two main camps: critic-based and critic-free.
Most people have probably heard of RLHF reinforcement learning from human feedback. That fits in the critic-based category, right?
Exactly. RLHF is a classic example. You train a separate reward model on human preferences, and that model acts as a critic, giving feedback to the main LLM policy. PPO, proximal policy optimization, is a super common algorithm used here. It's known for being relatively stable, but the downside is the computational cost. You're running and updating two models, the policy and the critic.
Okay, so powerful but resource hungry. What about the critic-free alternatives? Sounds like they might be more efficient.
They generally are, yeah. Critic-free methods work directly with that final sequence-level reward, like a simple correct or incorrect. No separate critic model needed. This is much less computationally demanding, and for RLVR tasks where you have a clear, objective reward signal, it can work really well. The paper specifically mentions GRPO, group relative policy optimization. It's a modification of PPO that DeepSeek R1 used. It helps reduce variance by normalizing rewards within groups of outputs, which apparently speeds up training quite a bit for these reasoning tasks.
Interesting. So potential efficiency gains there. What about learning from data you already have, not just the brand new stuff the model generates?
Right. That's where off-policy optimization comes in. These methods are great for sample efficiency. They let the model learn from older data that wasn't generated by the absolute latest version of the policy. You can reuse past experiences, which is super valuable. Often, what works best in practice is a kind of hybrid approach. Maybe start with some supervised fine-tuning, SFT, to get the model in the right ballpark, then switch to RL.
A warm-up phase, basically.
Sort of, yeah. Now, while we're optimizing, we also need to make sure the model doesn't go completely off the rails and start generating nonsense. That's where regularization objectives come in.
Correct. You need guardrails. KL regularization is a common one. It penalizes the model if its policy strays too far from a reference policy, maybe the original base model. But here's a fascinating twist for reasoning tasks. Some recent work, including stuff cited in the paper, actually argues for removing the KL penalty.
The thinking is that maybe the policy needs more freedom to explore really different, complex reasoning paths, new chain of thought structures that the original model couldn't find. It's a bit controversial.
So less constraint might lead to more creative reasoning.
Potentially. Another key regularization is managing length. Longer reasoning chains are often better, but they cost more computationally during inference. So you might use length penalties or techniques like stage context lengthening train on shorter problems first, then gradually increase the length, balancing depth and cost.
Okay, got it. Rewards, optimization algorithms, regularization. What about the data itself, the sampling strategy? What kind of examples do we feed the model during RL training?
Yeah, you need good data, good rollouts. Quality and diversity are key. The paper talks about dynamic and structured sampling.
Yeah.
Dynamic sampling is pretty clever. It adapts what prompts it gives the model and how much compute it spends based on how the training is going. Like if the model is struggling with a certain type of problem, maybe focus more compute there.
So it's adaptive, not just random prompts.
Exactly. And structured sampling goes further. It's not just what you sample, but the shape or topology of the reasoning traces. Think about organizing the different reasoning paths the model tries as a tree, maybe like Monte Carlo tree search. You can assign rewards at different nodes in the tree, giving denser feedback and guiding the exploration more efficiently.
Okay, that covers the core mechanics. Now let's wade into some deeper waters, the foundational problems. These are the big, open questions and debates shaping the field. First one, what is RL really doing here? Is it just sharpening skills the model kind of already had, or is it enabling true discovery of new abilities?
That's a really fundamental question. Theoretically, you can think of supervised fine-tuning, SFT, as mode covering, trying to learn all the patterns present in the training data. RL, especially with these optimization methods, tends to be mode seeking. It focuses the probability on the specific sequences that lead to high rewards. The paper leans towards discovery, citing evidence like DeepSeek R1 showing emergent reasoning skills that weren't explicitly trained. It suggests RL can genuinely unlock new capabilities.
So potentially creating intelligence, not just refining patterns. That connects to another bold claim, RL versus SFT. Generalize or memorize, the paper flat out states, SFT memorizes, RL generalizes. That's quite a statement.
It is pretty bold, yeah. But there's research backing it up. RL often performs better when tested on problems different from its training data, out of distribution. It seems to preserve the underlying structure better. SFT, especially if you train it too narrowly, can overfit and basically just memorize the training examples without really understanding the underlying logic. It can also suffer from catastrophic forgetting of its original abilities. That said, the practical consensus right now often involves both. Using SFT first to provide a solid base, then using RL to build that generalizable reasoning capability on top.
Right, the hybrid approach again. SFT for foundation, RL for robust reasoning. What about the starting point, the model prior? Weak and strong debate. Does it matter if we start RL from a raw-based model versus one that's already been heavily fine-tuned with instructions?
Well, it definitely matters. And somewhat counterintuitively, several studies, including DeepSeek R1 again, found that starting from a more basic, unaligned model actually worked better for RL. It seems like heavily instruct-tuned models might already be too constrained, too locked into certain ways of responding, which makes it harder for RL to explore and find those novel, high-reward reasoning paths. But it probably varies between model families too.
Interesting. So maybe less preconceived bias is better for RL.
Okay, next up, training recipes, tricks or traps. RL training is notoriously finicky. People use all sorts of engineering tricks, normalization, clipping, trimming rewards. Are these essential techniques or just hacks that hide deeper issues? That's a really hot topic. The paper points out a major problem in the field. Inconsistent experiments, missing details in papers, conflicting results about whether these tricks actually help universally. Models like DeepSeek Math and DeepSeek R1 actually argued for simpler recipes, using things like Critic-Free GRPO, suggesting maybe some of the complexity isn't needed. There's a strong call in the survey for more rigor-unified testing setups, using verifiable rewards to really validate whether a technique is a robust improvement or just something that worked once in a specific setup, tuning tricks into actual science.
A call for more systematic research. Makes sense. Final debate in this section. Reward type. Process or outcome? This goes back to the reward design. Is just knowing the final answer was right, outcome enough? Or do we need feedback on every step of the reasoning process?
This is the reward is enough debate, essentially. Outcome rewards are simple, scalable, especially for verifiable tasks like math. You just check the final answer. The risk, though, is the model learning to cheat finding the right answer through faulty logic. You might get answer first, hallucinate the reasoning later, behavior. Process rewards, giving feedback on each step, are more likely to lead to faithful, understandable reasoning. But getting that step-by-step human feedback is incredibly expensive and time-consuming, and might not generalize perfectly. So it's a big trade-off.
Cost and scalability versus faithfulness and reliability. Okay, let's switch gears slightly and talk about the training resources. What fuels these LRMs? What kind of data and environments do they need?
Well, the big shift here is definitely from just massive scale to focusing on quality and verifiability. For static corpora, the fixed datasets, we're seeing more specialized collections, things like DKBO and Limo for math, Cod Code or Leak Code datasets for coding. Crucially, these often include detailed reasoning steps, like chain of thought explanations, and ways to actually check the work, supporting that RLVR approach.
So, data designed for reasoning training. But static data has limits, right? You eventually run out, or the model just memorizes it. This must be driving the move towards dynamic environments.
Absolutely. Static data sets just aren't enough for the really advanced generalizable reasoning we're aiming for. The field is moving fast towards dynamic interactive environments. These environments can either generate potentially infinite new problems on the fly, or they allow the model to interact step by step, getting feedback throughout its reasoning process.
Can you give some examples of these dynamic setups?
Sure, the paper groups them nicely. You have rule-based environments like generating logic puzzles or code challenges that have clear deterministic rules. Then code-based environments, which are really cool, they can simulate actual software development, maybe by creating tasks from GitHub commits or letting the agent interact with coding tools. And game-based environments. Games are great for RL because they often have clear states, actions, and built-in reward structures. Think complex strategy games or science simulation worlds. These really push the agent to learn long-term planning. There are also model-based environments where models interact with each other or play games against themselves to generate training data.
Wow, quite a range. It really feels like moving from reading textbooks to actually doing lab experiments or playing complex games. To manage all this, you need solid RL infrastructure, right? The software tools to run these complex training setups.
Definitely. You need frameworks that can handle distributing the work, running the model to generate data, rollouts, and updating the model policy training, often asynchronously. The paper lists several open source frameworks like TRL, OpenRLHF, and others. These are built on top of the big LLM training libraries and provide the pipelines needed for RL, supporting things like agentic interactions, multimodal data, even multiple agents working together. They're the engine room for LRM development.
Okay, makes sense. So we have the theory, the components, the resources. Let's talk applications. Where is RL for large reasoning models actually making a difference today?
The impact is already pretty broad and growing fast. Coding tasks are a huge one. RL is helping generate code that not only looks right, but actually compiles and passes tests. It's used for competitive programming problems, but also practical software engineering, fixing bugs, improving code quality. We're even seeing agentic systems where the LLM can write, test, and debug code all by itself. Think systems like Kimi K2 or the latest coding models.
That's got to be transformative for developers. What about other kinds of agentic tasks, using tools, interacting with the web?
Yeah, that's another major area. RL helps LLMs learn to use tools effectively. Search engines, calculators, web browsers, even interacting with graphical user interfaces on a computer. Managing these interactions, especially when they involve many steps over time, requires things like asynchronous processing and memory, which RL frameworks are starting to handle better. Think automated research assistants.
So the LLM isn't just processing text, it's acting in a digital environment. What about reasoning across different kinds of data, multimodal tasks?
Right. RL is boosting performance here too, helping models reason about images, video, maybe even 3D environments, and generate outputs that combine modalities. It helps tackle tricky problems like ensuring numerical values mentioned in text actually match the image content, or generating coherent descriptions of complex visual scenes, pushing towards models that perceive and interact more like humans.
Very cool. And what happens when you have multiple LLMs trying to achieve a goal? Multi-agent systems.
That's MAS, yeah. RL is proving crucial for getting multiple AI agents to coordinate and collaborate effectively. It helps figure out which agent deserves credit for success, credit assignment, and optimize their joint actions. The paper mentions GRPO, for example, applying multi-agent RL concepts to improve how LLMs work together on tasks like co-writing or collaborative coding. It's about enabling effective AI teams.
AI teamwork, fascinating. And bridging the gap to the physical world, robotics tasks.
Yep. The same RL principles, like the GRPO algorithm from DeepSeek R1, are being applied to train robots specifically. vision-language action models. This allows robots to learn complex tasks through interaction with their environment, often with much less direct supervision than before. They can discover new ways to do things and generalize better to new objects or situations. A big step for robotics.
And finally, a really critical domain, medical tasks. How's RL helping there?
It's being applied carefully, of course, but showing promise. Improving medical image analysis, like VQA, diagnostic reasoning, and generating structured medical reports. Verifiable rewards and ensuring the model follows reliable reasoning paths are obviously paramount here. The goal is to build medical AI that is not just accurate, but also trustworthy and interpretable.
Wow. Okay, that was a whirlwind tour, but incredibly insightful. This survey really drives home that reinforcement learning, especially RLVR, isn't just another tweak. It feels like a fundamental shift. It's tackling the core reasoning limitations of LLMs and turning them into these more capable, large reasoning models.
Absolutely. It provides that crucial mechanism for learning from outcomes, for refining the process of thinking, not just mimicking patterns. It feels like a necessary ingredient for getting to more generally intelligent systems.
And looking forward, the paper ends with some really mind-bending future directions. Things like using RL right from the start during pre-training, not just fine-tuning. Or, get this, having AI dynamically co-design its own architecture and algorithms using RL. Or even using these LRMs to drive fundamental scientific discovery.
Yeah, those are the really big, ambitious frontiers. It makes you wonder, doesn't it?
Yeah.
If models can learn to reason, learn to learn, maybe even learn to design better learners, what does that ultimately lead to? How does that change the whole trajectory of AI development and, well, everything else?
It's definitely something to chew on, a huge potential shift. For anyone listening who wants to go deeper, we strongly recommend checking out the full survey paper. It's dense, but packed with details on everything we discussed: algorithms, data sets, the works. Consider it food for thought, or maybe even inspiration if you're working in this space. Thanks for joining us on AI Paper Podcasts.